Kafka broker was OOM killed every 6 hours. The heap dump showed 3.5 GB of unread message buffers. The root cause? Fetch.max.bytes was set to 50 MB per partition, and with 100 partitions, the broker tried to buffer 5 GB in memory, far exceeding the 4 GB JVM heap. Let's break down why this happened and how to fix it. Welcome to TheCodeForge. Before we dig into that production issue, let's design a distributed message queue. In this lesson, you'll learn how to design a distributed message queue that survives production, based on real-world incidents and best practices. A distributed message queue decouples producers and consumers across multiple machines, providing at least once delivery, ordering guarantees, and horizontal scalability. It's the backbone of async microservices communication. A distributed message queue is a partitioned commit log. Each partition is an ordered, immutable sequence of messages. Producers append to partitions, consumers read from them. Partitions live on different brokers, giving horizontal scaling. Ordering is only guaranteed within a partition. Use key-based partitioning to preserve order per entity. Here's how you produce and consume messages with key-based partitioning. The producer sends each order event with the order ID as key, ensuring all messages for the same order go to the same partition. The consumer assigns each partition to a separate thread for parallel processing. Durability comes from the commit log. Every message is written to disk on the broker before being acknowledged. Batching writes improves throughput. Replication factor of 3 ensures data survives broker failures. Never set ref equals 1 in production. Configure the producer with ax equals all for durability, enable. Idempotence for exactly once, and batching settings to balance latency and throughput. Consumer groups allow multiple consumers to split partitions. When a consumer joins or leaves, a rebalance triggers. Use cooperative rebalancing to reassign only affected partitions, reducing downtime. Configure the consumer with cooperative rebalancing, appropriate timeouts, and a reasonable max poll records to avoid rebalances due to slow processing. Exactly once semantics require idempotent producers and transactional consumers. The producer assigns a unique ID to each message, the broker deduplicates. The consumer reads and writes in a transaction. This adds latency, so use it only when duplicates cause financial loss. An idempotent consumer skips duplicates by checking processed message IDs. For exactly once, use transactions to atomically commit output and offsets. If producers outpace consumers, the queue grows unbounded. Implement backpressure by limiting in-flight requests, rate-limiting consumer polling, and setting retention limits on topics. Use a rate limiter on the consumer to control processing speed. Also set retention limits on the broker to prevent unbounded growth. Monitor consumer lag, request rate, error rate, and disk usage. Use Prometheus and Grafana. Alert on consumer lag 1000 for 5 minutes and under-replicated partitions. Set up Prometheus alert rules for consumer lag and under-replicated partitions. Use the CLI to check lag per partition. Distributed message queues add operational complexity. For low throughput, single server, or latency-critical scenarios, consider simpler alternatives like in-memory queues or database tables. This is the same issue we highlighted at the start. Here's exactly why the broker oomed. The consumer fetch.max.bytes was set to 50 MB per partition. With 100 partitions, the broker tried to buffer 5 GB in memory. Combined with replication threads, the 4 GB heap couldn't keep up. The fix was to bound memory per partition. Set fetch.max.bytes to 5 MB, fetch, max, wait, ms to 500 ms, and added a consumer-side rate limiter using Guava's rate limiter. This prevented buffer buildup and eliminated OOMs. Setting fetch.max.bytes too high per partition can cause the broker to buffer huge amounts of data, leading to OOM. Always bound memory per partition, not per broker. Using null key causes round-robin distribution, but can lead to hot partitions if keys are not well distributed. Use a composite key to spread load. Static group membership keeps partitions even if the consumer disconnects. If the consumer crashes, its partitions remain unprocessed until it reconnects. Avoid static membership unless you have a reliable failover mechanism. The article uses Cooperative sticky assigner for incremental rebalancing, which is available only in Kafka 2.4+. For older Kafka versions, the default range assigner, or round-robin assigner, triggers a full stop-the-world rebalance. If you must use an older version, consider setting session timeout high and using static group membership with caution, or upgrade to at least 2.4. The article mentions a dead letter queue for failed messages, but doesn't show how to implement it. Here's a concrete pattern. Send messages that exceed retry limits to a separate DLQ topic and alert on DLQ growth. The article shows an idempotent consumer using processedids in memory. In production, this set must be persisted, e.g., Redis or a database, to survive consumer restarts. Otherwise, after a crash, the consumer will reprocess all messages since the last commit, defeating idempotency. Use a bounded set with TTL to avoid unbounded memory growth. To debug consumer issues, check the consumer group status with the CLI. Look for rebalance logs and verify timeout settings. Monitor lag per partition to identify hot partitions. Let's run through some common interview questions. How does Kafka handle broker crash? Leader election from ISR, producers retry, no data loss. When choose RabbitMQ over Kafka? Low latency, complex routing, priority queues. What happens if consumer exceeds max, poll, interval, MS? Consumer kicked, rebalance triggered. At least once vs exactly once. At least once allows duplicates. Exactly once uses idempotent plus transactions. Hot partition fix. Use composite key to spread load. And a few frequently asked questions. How to achieve high throughput? Partition batch ax equals 1 multiple consumer threads. Difference between Kafka and RabbitMQ. Kafka, high throughput replay. RabbitMQ, low latency routing. How to ensure data durability. Ax equals all, idempotence, ref greater or equal 3, commit after processing. How to handle consumer failures. Session timeout triggers rebalance. Cooperative rebalancing minimizes impact. To recap, partition by key to preserve ordering. Always use ax equals all and enable. Idempotence for critical data. Monitor consumer lag per partition. And remember that distributed queues are overkill for low throughput, single server use cases. Ready to go deeper? Up next, design a distributed key value store, then design object storage, simple storage service, then design a proximity service. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.